Good morning all. So today we'll continue on whatever was covered in the previous recorded lecture which was shared with you. Uh, so we started the discussion on this analog electronic instrument, which is you can say an improvement over the conventional PMMC instrument, wherein we used the meter and the meter was directly connected to the voltage which we are trying to measure, right? So let's say E is the voltage that is being measured in this context. So we also discussed about what are the limitations of moving coil instruments, and the advantage electronic instrument offer over the moving coil instrument is that it offers high input resistance or impedance, you can say, and it is capable of amplifying low voltages. So in this case it is not, but in general we'll see later on that it is capable of amplifying low voltages and able to measure those. So let me quickly go through the emitter follower voltmeter configuration, where uh, the arrangement with the transistor Q1 allows us to achieve the high input impedance in a way that the input impedance observed by the voltage source, or let's say not voltage source, the network whose voltage we are trying to measure E. If you look at from this side, then the input resistance is E by IB. IB is the base current which is flowing through the transistor Q1, and the current flowing through the meter is IE, which is the emitter current. And we know the relationship between base current and emitter current is basically governed by the current gain associated with the transistor. So a typical example, if you take here, that if the current gain is 100, then the base current for the meter full scale deflection current of 1 milliampere will become, so IB in this case is 1 milliampere divided by 100, which is 0.01 milliampere, which is 10 microampere, right? Now, if you are trying to measure the input voltage, let's say maximum input voltage E, FSD is 10 volts. So your R input resistance is 10 divided by 10 microampere, which is 1 mega ohm. You see, it's quite high input impedance which is observed. If you remember our previous discussion, where the input impedance offered by, how much is the input impedance offered by the PMMC instrument based voltmeter? How much was that? It is the series combination of these two, right? And it is only 9.3 kilo ohm. But now with this arrangement, we have achieved the input impedance of 1 mega ohm. Why high input impedance is desirable? It is because it reduces the loading effect, right? So lesser and lesser amount of energy is drawn from the circuit which you are trying to investigate, right? So there is no very less loading effect. But where does the energy come from for driving the meter? So it comes from this external power supply VCC. Okay, so this is basically an active instrument, whereas PMMC is a passive instrument. PMMC assisted with the transistor based circuit, emitter follower circuit, basically is an active instrument which requires an external power supply. So that extra energy required to drive the meter comes from this source, and this is why the energy drawn from the circuit which is under investigation is minimized. So loading effect is minimized. That is the advantage. Okay. So we have calculated the load resistance, right? And how much is the meter current when 10 volt is applied here? So we have also calculated that if this is 10 volts, we know that when the transistor is conducting, voltage drop across base to emitter junction is around 0.7 volts. So this voltage at this VE is 9.3 volts, right? And when this is 9.3 volts, the current flowing through this is 1 milliampere, which is the full scale deflection current of the meter. So what does it mean? That this circuit, for this example, is capable of measuring voltage from 0 to 10 volts, right? 0 to 10 volts. Now, let us check like the way I had done the calculation. Please let me know that when the input voltage E is 5 volts, how much is the current through the meter? First of all, tell me how much should be the current through the meter, or how much current deflection it should show. For 10 volts, it is showing 1 milliampere.
0.5.
It should show 0.5. Now calculate it whether it is showing 5.5 milliampere. How will you calculate? Do the same analysis. It is now 5 volts. Voltage drop is 0.7. How much is the voltage drop here across V?
4.3.
4.3. So how much is the current flowing through the meter now? The total resistance RS plus RM is 9.3 kilo.
Less than
0.462 milliamp.
0.462 milliampere. So what went wrong?
the drop across VB did not change proportionately.
Yeah. So what does it mean? That you must have studied in signal systems, no? Linear system. Have you studied linear systems?
Yes, sir.
LTI systems you must have studied, no?
Yes, sir.
Right. So this is like y is equal to mx plus c. If this is your system, okay, is it linear?
No, sir.
No, sir.
No, right? Because of this term, isn't it? So this is what is happening with this VBE. So the system is not linear. This is non-linear. Okay, so there is an error in the measurement. So you have to somehow get rid of this 0.7 effect of this 0.7 volts. So even though we have achieved high input impedance, we have compromised on the accuracy. Okay, so this is where the practical emitter follower voltmeter comes into picture, which utilizes the similar approach as the previous circuit, but there is an extra circuit which is similar to the previous one, is also uh, used to remove the effect of the base emitter junction voltage. So here, as you can see, that if you simply focus on this part first, so this part is similar to the previous one. You see, just that there is a resistor which is connected here. So not in this case, but here it is connected, right? And the voltage which is being measured E is applied here at the base of transistor Q1. Now transistor Q1 and Q2 are of the same make, means they are the same transistor, same characteristics for both of them, right? Now what is done here is that you have the meter which is being connected along with the series multiplier resistor to increase the range of the meter, we have already seen, and the meter resistance, the internal resistance of the meter. Okay, and the current IR will flow through this. Now in this circuit, what is done is that we have to first calibrate the instrument. What does it mean is that first what we do is we set E equal to 0 volts. So when we set E equal to 0 volts, and one more important thing, the difference between these two is that you see here this circuit consisted of only one power supply, that is external power supply, that is VCC, positive, and this is the negative terminal. Now in this case we have two power supplies. One is positive power supply VCC, one is negative power supply VEE, and this is the ground potential 0 volt. Rather, I would say that it is a common terminal with respect to which these voltages are measured. So with respect to this is positive VCC, and with respect to this is negative minus negative VEE. Okay, right. Now when this is connected to ground, means let's say if I short circuit this, then we know that the potential E or the voltage E what I'm actually applying is 0 volts. Now when 0 volt is applied at the base of transistor Q1, whether Q1 will conduct or not. Whether Q1 will conduct or not. So what is the condition for the transistor Q1 to conduct? We saw that when this is positive with respect to this, then this base emitter junction will be forward bias and the transistor Q1 will go in conduction mode. At when this is at 0 volt, can it drive this base to emitter junction?
No, so unless the emitter has a voltage less than 0.
So if I want to have the voltage less than 0, in the current condition, it is the same. Is it true that this is a lower potential than this?
So could you repeat the question?
Is this node, okay, is it at lower potential than this node? You see, this is connected to which terminal? Minus VEE, right?
Yes, sir.
So let's say this is, in this example, we'll take this is 12 volt, this is minus 12 volts, right? So with respect to this is at lower potential. Okay.
Yes, sir.
So in that case, this transistor will conduct. This transistor will conduct, and the current will flow through this resistance, and of course, in this manner. Okay. Now, when this is at 0 potential, when this is conducting, what will be the potential at this position?
Minus 0.7.
Minus 0.7 volts. Now, how much is the voltage across R2?
VEE minus 0.7.
No, the current is flowing in this direction. No, so this is positive, this is negative.
Yes, sir. VE minus 0.7, sir.
Are you sure?
It will be minus 0.7 minus VE, right?
Correct. Yeah, you should go in that way. So what will be the voltage drop across R2?
Minus 0.7 plus VE.
So that is 11.3 volts, isn't it?
Yes, sir.
Right. So you can calculate the current I2, which is asked to you here to calculate the current I2 in this example. Fine. Now, what we will do is that in this case, to remove the effect of this 0.7 volts, which we observed previously that it is going to affect the accuracy of voltage measurement, when you connect this terminal purposefully to ground and this is at 0 potential, we know that this is at minus 0.7 volts. Now, in this transistor circuit, which is like a replica of this one, we'll add, so this is an adjustable terminal. It's a variable resistor R5, which we tune it in such a manner that the meter in that case, let's say there is some potential here. Okay, we don't know what it is exactly, at this moment. So if it is different than minus 0.7 volts, then it will show some deflection, right? Because of the potential difference, some current will flow through this. Some current will flow through this and it will show some deflection. So we'll adjust this variable resistor in such a manner that we'll see that the meter indicates zero deflection. Okay, so adjust R5 till meter deflection is zero. Okay, we'll do that. So first we'll do E is equal to 0, then adjust R5 till meter deflection is 0. What does it mean when meter deflection is 0? What will be the potential of this point?
Will be same as minus 0.7.
Minus 0.7 volts. Right, so meter is 0. So similarly, this is also conducting and the voltage drop across this will also be same. So when R2 and R3 are same, the current flowing through these two resistances will remain the same because the potential drop is again 11.3 volt in this case. Okay. Now we'll apply some non-zero voltage E, which we want to measure. Okay. Now previously, if you look at here, when E was applied here, the voltage across meter which was appearing was how much? E minus 0.7, isn't it? The voltage across this. So E was E minus 0.7. But in this case, now what we will do is when we apply E, what will be the potential at this point when E is applied?
E minus 0.7.
So in that case, it will be E minus 0.7. What will be the voltage across the meter?
E, if it is minus 0.7 on the other end.
Yeah, so E minus 0.7 minus 0.7, which will be E, right? So have you got rid of the effect of 0.7 volts? Right. So if you take the same example here, if you consider 10 volts for which you would like to design the voltmeter for 0 to 10 volts, if the meter current maximum full scale deflection is 1 milliampere, and then when you apply 5 volts across the meter, it will be 5 volts only. So that in that case, the meter will definitely indicate deflection of 0.5 milliampere. Here in this case, it was indicating 0.462 milliampere. Right. With this arrangement, we got rid of the effect of minus 0.7. One more advantage with this is that again the disadvantage with this is that we always assume that it is 0.7 volts, but in practice it may not be 0.7 also. Right? It may not be 0.7 also. It may change. It will change depending on the characteristic of the transistor, and it will change with the temperature. All these things. But since we are taking these two transistors of the same make here, they will have the same effect of temperature. So whatever it is, so in the calibration process, we have assumed that it is minus 0.7. It may be minus 0.6 also, but it doesn't matter to us because we will be adjusting R5 till we get meter deflection 0. So whatever it is here, whatever it is unknown, we are making sure that this potential is same as this. So the meter will only experience the voltage which is being applied. Right. So this is how the practical emitter follower voltmeter will work. So please remember, we are still working with DC quantities, DC voltage measurement, and at the same time the selection of RS, whatever we discussed previously in the PMMC based voltmeter design, remain the same. The analysis is exactly the same for RS. Okay, so if you look at only this branch, then it was similar to the previous one. With the involvement of these two transistors and other components, we have kind of increase the input impedance, and probably we'll see later on that it can increase the voltage measurement capability also. Okay, I hope this point is clear, this example. Now once, because we have now introduced this topic of two power supplies, one is positive, one is negative. Again here this circuit needed only one positive supply, it requires two now. So you can say that kind of increasing the complexity, or rather increasing number of components which are required to build this voltmeter. However, it comes with this advantage. So the important points are to understand is ground terminals and floating power supplies. Now you see at this time we use this symbol to represent the common terminal of the voltmeter. Okay. However, if you look at a circuit, let's say this is the voltage which is there, and the circuit has, if you look at this part, okay, this part. So this is the circuit, okay, within which we want to use the voltmeter to measure the voltages across different terminals. Now this is a simple circuit. It is a 3 resistance voltage divider circuit, and you would like to measure the voltage across these two. Okay. Now let's say I connect it like this. This is 10 volts. This is 1 k ohm, 1 kilo ohm. Okay. If I connected this terminals like this, and with the previous convention that we are connecting the, we are now let me say that this is terminal A, this is B. So here it becomes A and B. Now what I'm doing is I'm connecting this B to the voltmeter and connecting to the ground. What is the problem with this circuit? What is the problem with this arrangement? Will it be able to measure the voltage across RB? Huh? Will it be able to measure it across RB voltage?
Across RP, no, sir.
Why?
So because there's a ground at the negative terminal.
Yeah. So what is happening is we are now effectively short circuiting the volts, the circuit, right? See, now the current flow will happen like this. So we are completely bypassing this resistance, the effect of this resistance, which is not expected, isn't it? What is expected is it should measure the voltage across RB in the presence of RS. So with this arrangement, we are actually measuring incorrect readings, not because the voltmeter is faulty, but the way we are connecting the voltmeter, right? So this is why in the case of voltmeter, we use a different symbol to represent the common terminal. You see here, a circuit symbol for common terminal. This is the ground terminal for the external circuit of which we are trying to measure the voltage. So this common terminal is derived from the battery supplies or the power supplies from which we are getting these voltages VCC and minus VEE. Okay, so you have this battery, let's say, whose positive terminal is here, negative terminal is here, another battery, positive terminal, negative terminal. The common terminal is derived by connecting negative terminal of one source with the positive terminal of other source. Okay, so this becomes my common terminal whose potential is 0 volts with respect to these voltages, of course, with respect to these voltages. And the common term, as you can see here, like power supply is there. Either you can use battery or you can use external power supply in your lab. Connect the negative sub terminal of one with the positive, and this becomes your common terminal. And this negative terminal of the voltmeter is connected to the common terminal, not to the ground. Okay, not to the ground. So these are basically known as the floating power supplies whose terminals are floating. They are not grounded. Okay, the problem with grounding is we just discussed that it is going to completely change the behavior of the circuit itself, because we are providing a you can say kind of extra path or separate path for the current to flow, right? So these voltmeter supply voltages, these are supposed to be are kind of considered to be floating in nature because they are not connected to ground. So we have to focus on the common terminal here, and this should be avoided. This connection should be avoided. Okay. Now you tell me when this is connected like this. So this is my voltmeter. If I connect it like this, what will be the potential of this terminal? Common terminal. Remember, this is connected to common terminal. And where this common terminal coming from? So this voltmeter requires positive VCC and also requires minus VEE, and there is a common terminal with respect to which these two are defined. So this is connected to the common terminal. What will be the potential of this common terminal? First of all, you tell me, is it a correct, is it a complete question or not? When I say potential, we should ask with respect to what? Okay, so with respect to this ground, what will be the potential of this common terminal? Will it be zero or non-zero? Will it be zero or non-zero? Yeah, you can make a guess. Hello?
Non-zero.
Non-zero. Why?
Like I will get the potential across RC.
Correct. So this potential will appear here as a common terminal voltage or potential with respect to ground. Okay. But this is common for this. So supply voltage to VCC still remains VCC only. Okay. So there should not be any confusion that the VCC is with respect to this. So whatever the potential of this with respect to ground, it doesn't matter to us. It is a common terminal for the power supplies, and all the internal connections here are made with respect to that. Okay, in the voltmeter. So that is the way we make sure that voltmeter will actually give the voltage drop across RP. Okay, if I do this, it is going the voltage drop across this entire thing. Rather, it is basically short circuiting. So it is basically disturbing the system, completely loading the system. So this is how we basically avoid the loading effect. So this need to be understood. Whenever you see these positive and negative supplies, you should remember. You see now in this the terminals, common terminal is shown with different symbol. Okay, fine. So instead of this extra arrangement that which we made to increase the range of the voltmeter, one can even increase the range by this arrangement, which is known as input attenuator. So what is done here is that the input voltage which is being measured is first divided by this 4 resistance assembly which is connected in series, RA, RB, RC and RD, and these different values are there. These different values are such, so you see that this part is exactly the same what we discussed previously. So we are now discussing this part. Okay, so when you look at this part of input attenuator, whatever is the input voltage E is being divided here, and you have this single pole multiple throw switch which is basically selecting the range which you would like to measure. So when at first position, the range is 1 volt, 0 to 1 volt. at the second position, it is 0 to 5 volts, 0 to 10 volts, and T 0 to 25 volts. These are the different ranges you can select by choosing one of the terminals, one of the switch positions, right? So when it is at this position, the range is 0 to 1 volt. So the entire voltage will appear across this. So when you are applying maximum voltage of 5 volts and like choose this switch, what is happening is that the extra voltage is dropping across this resistance, and whatever will come here is 1 volt only. Okay, 1 volt only. And when you connect it here, the extra voltage is dropping across the series combination of this. You can do the calculation that when 10 volt is applied in this range, then the potential here will be 1 volt. So every time you select the switch, depending on the range which you want, whatever you get here is always 0 to 1 volt. Okay, 0 to 1 volt. Now this circuit is basically assisted with an FET component which is applied, which is connected at the input stage of the voltmeter. Basically, it is a JFET source forward circuit which is shown here, which offers, so this FET based circuit offers very high So have you studied FET in your basic electronics course? Hmm?
No.
Field effect transistor. Have you studied this?
No, sir.
No. Okay.
No.
Okay. Okay. It is like it is the construction, the physical construction of this is different, but it is basically field effect transistor. It is transistor only, but it is a voltage driven circuit, whereas the transistors are current driven circuits, current driven devices. So probably in your basic electronics course or other course, you will definitely cover this part. So we'll not focus on this right now, but just for our purpose, just remember that FET is a device which offers very high input impedance. Okay, very high in mega ohms. So it offers very high input impedance. That is why we are choosing this as a device at the input stage of the emitter follower voltmeter circuit. Now the operating condition for FFT to conduct, you see, if this JFET is used to drive Q1. This is a transistor only, so it is used to drive Q1. To drive Q1 to conduct Q3, the condition is that VGS should be means gate and source. So this is a gate terminal, this is a source terminal. Okay, so the VGS, the potential drop, the voltage drop across gate to source should be minus 0.5 volts. Okay, minus 5 volts. Sorry, not 0.5, 5 volts. Okay, now initially imagine that we are using 0 to 1 volt as a range which we would like to measure. So the switch is at position at this position. Let me say A, B, C, and D. It is at position A. Okay, so gate to source voltage should be minus 5 volts to conduct it. So when this is at 1 volt, gate is at 1 volt. When it is conducting, what will be the potential at S? What will be the potential at S with respect to common terminal? Consider that FET is conducting and this condition is satisfied. VGS is minus 5 volts. What is the voltage at this point? Node. Gate is at 1 volt. So VG is 1 volt. VGS I want is minus 5 volts, which is there. If I consider, then what is VS? Hmm?
6 volts.
It is 6 volts. It is 6 volts. Now, if you look at the previous arrangement which we made to see the working principle of this voltage emitter follower, that we basically short circuited this initially, isn't it? We connected the supply voltage to 0 for the calibration purpose, so that the meter will indicate 0 volt in that case. So at that in that case, the gate voltage was 0 volts, right? So for the transistor to conduct, this will become 5 volts, right? The base of Q1 will be at 5 volts. So we make sure that this voltage is this node is at same potential as this node, will adjust this so that this will also come at 5 volts, and the since two transistors are same, this will be at 4.7, this will be at 4.7, and there won't be any what you can say current which is flowing through the meter in the calibration stage when this is 0 volt. When this is 1 volt, this becomes 6 volts. This becomes 6 volts, and this becomes 6 minus 0.7, 5.3 volts, and this was at 4.3 volts initially. What is the voltage drop across meter now?
1 volt.
1 volt, which is the actual which we would like to measure. Okay, this will appear. So if you connect any range now, since anyway by this voltage divider arrangement, only 1 volt will go corresponding to the maximum value of the voltmeter range, whether it is 0 to 1 volt, 0 to 5 volt, 0 to 10, or 0 to 25. The same discussion will follow. Same will come at the same conclusion that this will be always at 1 volt maximum for full scale deflection, right? So this is how the voltmeter range which can be changed and FET input can be applied. So don't worry about the working principle of this. Anyway, you will study this in detail later on. Now, okay, so at 10 volts, the switch is at this position. So let's take an example here. It's this position. It is still 1 volt only because of the voltage division, and again we'll see that it is at 5.3. This is at 4.3. You'll get the deflection. At when you apply 7.5 volts here, what will be the meter current in that case? The maximum full scale deflection current is 1 milliampere. First of all, is it linear circuit or non-linear? Is it linear or non-linear? So one was non-linear, this is linear, and we have simply extended it the voltage range and connected a high input impedance FET stage. Apart from that, this is linear only, right? So for 10 volt full scale deflection, if it is giving full scale deflection current of 1 milliampere, for 7.5 volts, how much should it give?
0.75.
0.75. So you can cross check it whether it is giving 0.75 by recalculating. In fact, you have to use these values to calculate the potential at the gate. Okay, how will you calculate? So in that case, VG will be if it is at this stage, then it is RC plus RD divided by RA plus RB plus RC plus RD into 7.5 volts will be VG. Okay, so you have to consider VGS as minus 5 volts. Calculate the potential at the source, calculate the potential at this node, and this is always at 4.3 volts after calibration, and find out the voltage drop across this. You will see that it will be 0.75 volts. Okay, so since these values are given, I leave it to you to substitute it here and probably follow it. Okay, and you will know that it will be 0.75 milliampere, which will be shown by the meter. So it is a linearly scaled device. Fine. one can now, till now, we were only discussing about the voltages which can be measured of a range which is probably higher than 1 volts, right? The minimum was 1 volt here, then 5 volts, 10 volts, and 25 volts. How about voltages which are in the range from 0 to 100 millivolts? Okay, low voltage measurement. So if you use them directly with the meter, this voltage is not good enough to drive the PMMC instrument because they require some significant amount of current, right? So what is being done is, first of all, you increase this voltage, whatever is being measured, you increase the voltage level by using amplification, that is voltage amplification. You perform voltage amplification, and that amplified voltage you measure. And if you know the amplification, then you can easily do the calibration, right? So in this case, the circuit, as you can see, it is now emitter coupled amplifier. Okay, so you can see that the meter here was connected across the emitters of the two transistors. In this configuration, it is connected at the collector terminal. Okay, and the emitters are connected together with emitter resistance Re, and it is connected. Emitter is still at negative potential, collector is still at positive potential, and the input is still applied at the base of transistor Q1. Okay, and Q2 is, in this case, is maintained at common terminal potential. Okay, common terminal potential. Now, if you see that if E is 0 in this case, then these two transistors are at the same condition, right? So the current flowing through this IE1 is equal to IE2, and since I1 is equal to I2, IC1 will be equal to IC2. So the potential at this and this are equal, so meter will indicate 0 volt, sorry, 0 deflection, right? But when E is non-zero, let's say E is positive, then Q1 will conduct, right? Q1 will conduct. It will increase the potential at this node, right? It will increase. So initially, when it is 0, this is at minus 0.7 volts. But when it is E, it is E minus 0.7 volts. So it will increase for the positive value of E. Now, when this has increased, what will happen is that this is still at 0 potential, right? So the current in IC Q1 will increase, but the current in Q2 will decrease because of the decrease in the potential difference across VBE. So for E greater than 0, IC1 will increase, IC2 will decrease. Okay, this arrow I'm showing about the magnitude, okay, not the direction. IC1 will increase, IC2 will decrease. When IC1 will increase, what will happen to the potential at this node? Can someone tell? Will it decrease or increase? With increasing IC1.
It will decrease, sir.
Sorry?
Because if IC1 increases, then RL1 will take more voltage, right?
Right. So the potential at this will decrease, right? And due to decrease in IC2, the potential across RL2 will decrease, and the potential at this will increase. So you will see that the current will flow in this direction. Okay, the meter should be connected in that manner. Remember, PMMC is a polarized instrument. Okay, so for the voltage measurement, this will be connected in this manner. Okay, now this RL1 and RL2 are load resistances which are properly chosen so that sufficient potential difference is developed here, and so the potential difference developed is equal to the magnified voltage of E. The voltage magnification will occur due to the load resistances and the connection which is made at the collector. Okay, so it will simply follow because it is a linear amplification. You can easily do the calibration. Okay, so in that case, the initially, if you see, whatever was applied here was appearing across this meter, but it will not be the case here. The potential across this will be magnified version of this E, because we are measuring it for low voltage measurement along with voltage amplification, right? So that is the simple working principle of this thing. And in fact, what you can do is for zero adjustment, like if you want to like when it is at zero potential, if you want to maintain the zero current through this meter and zero deflection, this alternative arrangement is also provided, where if you see that here, how did we do the voltage adjustment? By connecting a potentiometer at the base junction of Q2. You can do the same thing here as well to achieve the zero adjustment, but the easier adjustment is provided here, where you have another resistance R3 which is connected in this manner and which is having a variable terminal to which the VCC is connected. Okay, so when you move this terminal, this arm in this direction, more amount of R3 is being added in series with RL1. Okay, and if you move it in this direction, more amount of R3 will be added to RL2, and at the center position, R3 by 2 will be added in series. Here R3 by 2 will be added in series. So you have to make that. Remember, these values are not exact, no, that we cannot rely on the exact values provided by the manufacturer. There are always tolerances. So one has to do the manual zero order adjustment. So you can simply tune this so that the two branches here, these two branches are reflection of each other, and we achieve the same potential drop potential at across the meter when E is equal to 0. Okay, this is how the differential amplifier voltmeter based circuit works. So we have seen, you see that starting with a very simple emitter follower voltmeter, we made it slightly complicated by adding another transistor circuit to remove the effect of 0.7 volt. Then we have also included the voltmeter range selection arrangement along with the FET input stage, which increases the input impedance, and we went further ahead by not only measuring the voltages of higher ranges, that is 0 to 1 volt or 5 volts or 10 volts, but we can now measure the lower voltages also by achieving the voltage amplification offered by the emitter coupled amplifier circuit. This can be much easily done nowadays. Instead of these transistor based discrete components, one can basically use operational amplifier to build voltmeter circuits. So although you have not studied FET in your BTech, in your first year basic electronics course, I hope you have some exposure towards op-amp circuits. Are you familiar with op-amp?
So we did have a few lectures in EE101.
E101, right? Some basic you must have done, right? Yeah.
Yes.
So what
basic.
is the basic characteristic of an op-amp?
The differential amplifier.
So it is a differential amplifier. So what will be the output voltage? How can you express it?
Proportional to V plus minus V minus.
V plus minus V minus into gain of op-amp, right? How much is typically a gain of op-amp?
Infinity.
Sorry?
Infinity.
So it is very high. A is very high. So for a very small difference also, it will give some significant voltage. So again, the supplies are shown here. You must have studied that. It also comes with it requires for its operation two power supplies, positive and negative both, with respect to the common terminal of the source. Then this is the basic characteristic. So this is achieved, and one more important characteristic is that the input impedance of op-amp is how much? is infinity ideally, but is very high, right? Very high. So these features are key to design of voltmeter, because we know that would like to have a circuit which takes very less amount of current, right? So you see the input attenuator is same as shown previously. A, B, C and D, 4 terminals. You can select the range according to the voltage division. So this voltage EB will appear here, which we are actually measuring. Okay, this is EB what we are measuring, but we'll calibrate it in terms of E. Now, since and okay, what is the bias current of an op-amp ideally? How much is the current flowing through this? Ideally, idle op-amp.
0.
0, right? 0. Practically it is very small, probably in very few microamperes or nanoamperes. A very small amount of current will be drawn from the circuit which you are measuring. That's why it offers very high input impedance. Okay, and the arrangement we are using here for the op-amp is voltage follower network, for voltage follower circuit. So you can see that as the name suggests, the output voltage follows the input voltage. Now here the input is applied at positive terminal. Here it is EB. Okay, is EB. So if you can apply this logic in this case, that your output voltage is A into V plus minus V minus. So this output terminal is basically connected in negative feedback mode directly to the negative input terminal of the op-amp. So what is the potential at this node?
It should be the same.
It should be the same as that of
V minus.
sorry.
So could you repeat the question?
What will be the potential at this node, at the negative input terminal of the op-amp?
Same as V plus.
Same as? Should be same as V plus. What does it mean? See, op-amp, whatever circuit you take, if you want to analyze the performance or try to build also an op-amp circuit, one can easily see that op-amp will always try to bring these two potential at the same level as much as possible. Okay, as much as possible. So if you see this, that V plus minus V minus is V0 by A. When A is very large, even though V0 is significant, when A is very large, V plus is almost equivalent to V minus, because this difference will be almost 0. So when V plus is V minus is almost equivalent to V plus, what is V plus here? EB. So what is V minus? Is EB, right? But what is V minus? What is V minus? Is V0, right? That is how we have connected it. Negative feedback mode. So what is V0 then? What is V0?
EB.
EB. You see, now EB will appear across the meter as it is. What have we achieved here? Very high input impedance. Okay, very high input impedance, and advantage with very high input impedance is very low loading effect. Very low loading effect, because almost nothing is drawn from the circuit which is under investigation, right? So this is why, since the output follows the input, that's why it is known as voltage follower circuit, and this arrangement is used for voltage follower based voltmeter design. Okay, it's a very simple approach. You can simply extend it to include the amplification as well. Okay, so why only provide EB? Can I apply some magnified value of that? So what is this? This is non-inverting amplifier. Have you studied this non-inverting amplifier? Have you studied this part?
Don't remember that much, sir.
Yeah,
Sorry?
Don't remember that much, sir.
Don't remember. Okay. So again, apply same analysis. V positive, V negative. Huh? What is V positive? Is E in this. Now the feedback is taken from the output, but not directly as in the case of voltage follower network, but it is done through a voltage division. So a fraction of output voltage is fed back to the input, not the entire output voltage. Okay. Now what is V minus?
VR3.
VR3. What is, and how much is VR3?
I4 into R3.
Huh?
Or R3 by R3 plus R4 into V out.
R3 divided by R3 plus R4 into
V out.
V out. Right? V out. And as I told you that op-amp will always try to bring these two potential at the same level. If I use that analogy, E will be equal to, or rather I would say E means V input is equal to R3 divided by R3 plus R4 into V out. So what is V out?
R4 plus R3 divided by R3 into E.
So R3 plus R4 divided by R3 into V in, which is in this case is E. Right? So isn't it non-inverting amplifier formula you must have studied? You remember now?
Yes, sir, slightly.
Yeah. So this is the output voltage, which is the magnified version of this. Because you see R3 by R3 is 1, so it is R4 by R3, which is always greater than 1, greater than 0. So this quantity which is being multiplied with E is higher than 1 always, right? So output voltage will be higher than the input voltage, and that output voltage is now driving the meter. You see? So if the input voltage is, let's say, 0 to 100 millivolts, if you set the value of R4 and R3 such that you can extend it to 1 volt, is 100 millivolt, then you can drive the meter, right? So you are able to measure low voltages as well, right? So more about this in the next class. Thank you.
Thank you, sir.
Thank you, sir.
Sir, hello, sir.
Yes, yes.
Sir, in the previous exam, a question which is given at minus 3 dB frequency, pe, omega is 25 radian per second. And we have to find the time constant. Then we have calculated time constant 1 by omega. Then why it is wrong?
Yes, sir, same question.
I think you have taken the formula as 10 log of m, right?
Yes, sir.
It should be 20, no?
No, sir. 10 log.
For power it is 10.
Sir, we have to calculate only time constant, na? Because time constant, and we know that the at minus 3.
Which question you are talking about? I'm talking about the tau calculation, and after that the first question. Which question was that?
First the tau, then after phase delay.
Yes, sir. Yes, sir.
But in the computation of tau, you have to utilize the formula related to the magnitude in dB, isn't it? Which was given as minus 3 dB. So what is the magnitude?
Minus 3 equals to 20 log V out by V in, right?
Yes.
So that we used.
Yes, sir, that we used. That's the same formula.
Yes, okay, I will cross check it again. Yeah.
Sir, actually,
can you upload the solutions also?
Yeah, I will upload the solution today. Yeah.
Sir, for all the questions, please.
Yeah, all the questions. If we have already prepared it. In fact, I should have uploaded it yesterday only, but I will upload it today after the class. Yeah.
Okay, sir. Thank you, sir.
Thank you.